Hi, this is Chuck. In this particular video, we are going to look at taking derivatives of trigonometric functions and doing some optimization with trigonometric functions. All right, as we get started in this section on computing derivatives of trig functions, I want to first revisit something that we looked at earlier in the course, and that was that we can take the function e to the x and we can write it as a Taylor series expansion, which looks like this, where we have x squared over 2 factorial plus x cubed over 3 factorial plus, and it just keeps going. The same thing or a similar thing can be done with cosine and sine. Now, the nice thing about writing them out like this is you can then see how the derivatives relate and come about. The way that you can define cosine is that cosine of x is going to be equal to 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. And this continues to alternate plus minus all the way to infinity, only containing even powers of x. And you may look at the first term here and say, well, wait a minute, there isn't any power of x there. Actually, there is. This is x to the 0 power over 0 factorial. But 0 factorial is defined as being 1, and any number to the 0 power is 1, so that's considered to be 1 over 1, which is 1. So there's the first term for cosine. For sine, it's similar. If you want to define sine using a Taylor series expansion, it works out to be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. And this continues alternating signs all the way to infinity as well. Okay, so how does this help us? Well, let's first consider the derivative of cosine. So if we're going to do the derivative of cosine, that means that we're going to take this function that we have here, this cosine, and see if I can copy this down. So we're going to do that, and this is going to be equal to the derivative of, and we're going to have that very same function back. We're just going to define that once again as being the 1 minus x squared over 2 factorial plus x to the 6th, on like that. Okay, so how does this work out? Well, if we take the derivative of this term by term, what we're going to wind up with here is that the derivative of the cosine of x is going to be the derivative of 1, which is 0. Now, you need to be mindful here. If we're looking at this x squared, 2 factorial is 2 times 1. So if we take the derivative, we have 2x over 2 times 1. The 2's cancel, so we have 0. Then we're going to have minus x. Then we're going to have plus. We have an x to the 4th over 4 factorial. Well, x to the 4th over 4 factorial is 4 times 3 times 2 times 1. So the derivative is going to be 4x cubed over this 4 times 3 times 2 times 1. The 4's will cancel, and this gives us x cubed over 3 factorial. And this continues right on down the line. This is going to become minus x to the 5th over 5 factorial, which almost looks like something you've just seen. If you take a look at the definition of sine, notice that it's a positive x, the minus x cubed, a positive x to the 5th. So this can be rewritten if I factor out a negative and I drop that 0 as x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus, which really gives me then negative the sine of x. So what this says is if I take the derivative of cosine, what I'm going to wind up with is negative the sine. Now, a similar move can be used to compute the derivative of sine. Okay, so remember, sine is defined as this right here. And if we go and take the derivative of it, what we're going to have is that the derivative of the sine of x is equal to the derivative of this Taylor series expansion of the sine of x, which is right there. Okay. Now, just like we did with cosine, we can term by term take the derivative of sine, and what we're going to get here is that the derivative of the sine of x equals, well, the derivative of x is going to be 1 minus, just as we saw above, we are going to have 3x squared over 3 times 2 times 1, which will give us x squared over 2 factorial, plus, when we take the derivative of this term, we're going to wind up with 5x to the 4th. Well, the 5 will cancel, and this is going to give us x to the 4th over 4 factorial minus, and then this next one's going to be x to the 6th over 6 factorial plus, and it's going to alternate signs. And you may recognize that as being something that we saw a little bit earlier up here. Oh, look, at the top of the screen, that winds up being cosine. So what this gives us then is that the derivative of sine is equal to cosine. Now you've got to be careful here, okay? Notice it's not negative the cosine. The derivative of sine is cosine. However, looking up at the top of the screen, the derivative of cosine is negative sine. So be careful with that negative sign, okay, that you don't get things mixed up. From this, we can move on and then compute the derivative of things. For example, the derivative of the tangent of x. Well, that's the same thing as saying, well, let's take the derivative of the sine of x over the cosine of x, because tangent is sine over cosine. However, this is going to wind up being a quotient rule. First off, I'm going to do the cosine squared in the denominator. That's pretty easy. Might as well get that done before it gets overlooked. Now remember, we're going to do the derivative of the numerator. The derivative of sine is cosine. So we're going to have cosine of x times the denominator, which is the cosine of x, minus the numerator, well, that's the sine of x, times the derivative of the denominator. Be careful, this is negative the sine of x. Okay, so this gives us then cosine squared of x minus a minus on the sine is going to give us plus sine squared of x over cosine squared of x equals, where do we go from here? First off, do not cancel out those cosine squareds like that. That is not something you're allowed to do. Algebraically, that is a mistake. You can only cancel something in the numerator and the denominator if every term has that factor you're canceling. Notice in the numerator, the sine squared doesn't have a cosine squared. But if you go back to the Trig review part 1, you may recall that cosine squared plus sine squared is just another way to say 1. And this winds up being 1 over cosine squared of x. Wonder what that gets us. Well, this can be written as, if you'll recall, 1 over cosine has a trig function assigned to it. And what we really have here is 1 over cosine times cosine. 1 over cosine is secant of x times secant of x, which tells us then that the derivative of tangent is going to be secant squared of x. You can, and I'll leave it to you, do the derivatives for cotangent of x. We're going to have the derivative of the cotangent of x. And if you compute that, following similar pattern to what we did here, you'll get cosecant squared of x. If you compute the derivative of secant of x, that's going to give you the secant of x times the tangent of x. Now to set this one up, remember secant is 1 over cosine. And you'll just apply the quotient rule to that. You'll need to use some of the trig identities that we looked at earlier, but you can work that down to being secant times tangent of x. And last but not least, the derivative of the cosecant of x is going to be the negative cosecant of x times the cotangent of x. These others may be handy, but the three that we will use the most often are the fact that the derivative of tangent of x, let me write this like this, is secant of x, and the two up above here, where we have the derivative of cosine is, here it is, the derivative of cosine is negative sine, and the derivative of sine is cosine. So those two, along with the derivative of tangent is secant squared, are going to be the three derivatives we're going to be referencing most frequently. Okay, with those basic derivatives defined, let's take a look at computing the derivative of some different functions. So for example, suppose we have the derivative of the sine of 7x. Well, this is going to be a chain rule because we have an inside function, the 7x, and an outside function, the sine. And what's going to wind up happening is we're going to take the derivative of the outside first. The derivative of sine is, that's right, cosine, times the argument inside. Then, after you have that done, now you multiply it times the derivative of what's inside, and this will give you 7 times the cosine of 7x. If we had something like this, the derivative of secant cubed of, let's say 5x equals. First, realize that this can be written as the secant of 5x cubed, and right away you can spot hopefully that, yeah, that is a chain rule once again. So what I'm going to do is I'm going to first record the derivative of the outside, leaving the inside alone. So I'm going to leave this secant of 5x alone and only work with the 3 in the exponent, which will come out front as a coefficient, times, or then with the exponent reduced by 1 to give us an exponent of 2. Now, we do the derivative of the inside. Well, this is going to be the derivative of secant of 5x. This, once again, is a chain rule. Okay, so to get this to work, we're going to take the derivative of secant. Well, recall the derivative of secant is the secant of 5x times the tangent of 5x. So we've done the secant part. Now we need to do the derivative of the argument, which is going to be a 5, which I could slide up front there like that. And what this is going to give me then is I can take the 5 times the 3, and I'm going to have 15. Now notice what we have here. We have the secant cubed of 5x times the secant of 5x times the tangent of 5x. Some of this stuff will multiply together. What we're going to wind up with is the 15 will stay there, but we have secant cubed times secant. So that's going to give us secant to the 4th of 5x times the tangent of 5x. And that finishes that one out. That one took a little bit of work. What if we had something like the following? Suppose you were asked to compute the derivative of x squared times the cosine of, let's see here, 3x. First, realize that this is a product rule. Do you see it? You have the x squared times the cosine of something. So we're going to have our first factor that we'll call f, our second factor that we'll call g, and wow, it's been a little while since we've done a product rule. It's going to be f prime g plus f g prime. Well, f prime is going to be the derivative of x squared, which is just 2x. G, that means we just copy down as cosine of the 3x. Remember to bring the plus down. Then it says here I want to just copy down f. So I'm going to put down an x squared. Then I have to take the derivative of g. Well, that's the derivative of cosine of 3x. That's going to be a chain rule. The derivative of cosine is going to be negative sine of 3x. Then I take the derivative of the argument inside, in other words, take the derivative of 3, which is going to give me a 3. I can rearrange this a little bit, and this becomes 2x cosine of 3x. I'm going to bring this 3 up front, and it's going to give me a negative, because I have plus and minus, 3x squared sine of 3x, and there you have it. Be sure that you practice a number of these derivatives because they're similar to what you've done in the past, but it's with a new function. So you need to get used to thinking about sine, cosine, what's the derivative of sine, things of that nature. Since we're going to be working with these trig functions, it's going to be useful to keep in mind what they look like and how things will alter depending on where you might have a coefficient in the function. So let's take a look at something like the following. Let's say we're given a function y is equal to a times the sine of b, and this b is going to be multiplied by x minus c over b plus d. Looks like a lot of letters laying around there. We could, in place of the sine, put cosine. So either of those two trig functions will work there and will be interpreted in the same way. A, B, C, and D are going to be constants, things like 2, 3, 4, 5, 6. So for example, we could come up with something like y is equal to 2 times the cosine of, let's say 4 times x minus 0 plus 3. So you can see that in place of A, B, C, and D, you can have numbers. And we'll come back to something like this in a few minutes. But first, let's talk about what each of these coefficients does. A is going to impact what's called the vertical stretch. In other words, it's going to talk about how tall will this function get. How tall it gets is the amplitude. Okay. The second thing we're going to look at is B. B is going to talk about the horizontal stretch. In other words, does it make the graph longer or does it shrink it up? Okay, it depends on if b is greater than 1 or less than 1. This is also useful for developing or determining what the period is. We talked about the period of a trig function in the previous video. The period is going to be equal to 2 pi over b. That'll be important for developing graphs. C is going to wind up, well, let's put it like this, c over b, because we do wind up with a fraction inside there. This is going to be the horizontal shift. This is going to tell you, do we take the whole graph and move it to the left or to the right? If the c over b is negative, that means we move the whole graph to the right. If c over b is positive, that means we move it to the left. The last value we need to consider here is d. It gives us what's called the midline. This also is the vertical shift. It talks about how much is the graph moved up or down. Okay, so let's look at something like this. Let's say that we have the function y is equal to 2 times the cosine of 4 times x minus 0 plus 1. First thing I'm going to do here is I'm going to identify what A, B, C, and D are. And in fact, I'm going to reference back up to this table up here as we go. Okay, A is going to equal 2. This is the amplitude. It tells us how tall the wave or the graph is going to get. B, okay, and you may say, wait a minute, what's B? B is right here. It's going to determine the horizontal stretch or the period of the thing. So in this case, B is equal to 4, which means we have a period of, let's see, it's going to be 2 pi. If we look, here it is, 2 pi divided by whatever that B value is. So in this case, it's going to be 2 pi over 4, which is going to be pi over 2. So this is going to tell us that the whole wave action, cosine going like this, is going to take place in the space of a length of pi over 2 units. We'll have to deal with that. The horizontal shift, if we look at the value of c over b, notice in our problem here, c over b is going to be 0. This means that we have a horizontal shift of 0. Well, that makes it easier. We don't have to move the graph to the left or to the right. And the last thing we're going to do is we're going to identify what d is. And for this particular problem, d is going to be this value that we add at the very end. Now what that's going to do is it's going to add 1 to every single number that comes out of that cosine. So every value is going to get moved up 1. This means that the whole graph is going to be shifted up 1. So we wind up with a vertical shift of 1. Let's take a look at how this actually affects the graph. I'm going to do a series of graphs. We're just going to step through it, one of these factors at a time. So first thing I'm going to do is I'm just going to do a quick graph of what are we starting with? Well, we're going to start out with y equals cosine of x. Cosine goes up to 1, down to -1. The full length of one period is 2 pi. And we have here pi over 2, and over here 3 pi over 2. When we graph this, at 0, cosine is 1. At pi over 2, cosine is 0. At pi, cosine's -1. Then it's back to 0. and back to 2. So what the graph looks like in this case is something like that. So there's the graph that we start out with. From there, we're going to start implementing some of the factors for our particular function. So we're going to next look at the cosine multiplied by 2. That's going to take each of the y values and make them twice as big as what they were. Well, what that means is where y was 1 before, it's going to go up to 2. Where y was -1 before, it's going to go down to -2. We're still going to have our pi, our 2 pi, and then we're going to have our pi over 2 and our 3 pi over 2. And what's going to happen now is it's going up to a +2, 0, -2, 0, back up to 2. What that coefficient of 2 out front does is it actually makes the graph taller. So there's what you wind up when that particular characteristic is implemented. The next one that we're going to wind up with is we're going to put in the y is equal to 2 times the cosine of 4x. What the 4 actually does is it causes the graph of the function to go through the entire set of values 4 times faster. What this does is it tells us that the period, and we've already figured this out, is going to be pi over 2. So when I go to set up the graph this time, instead of going over to 2 pi, all I'm going to do, I'm going to keep my graph going up to 2, going down to -2, but I'm only going to go over to pi over 2. Half of that is pi over 4. Half of that is pi over 8. And then between pi over 4 and pi over 2 is 3 pi over 8. So what it's doing is, instead of needing to go all the way over to an x value of 2 pi, the entire graph will be displayed by the time x achieves a value of pi over 2. So we're going to maintain the same amplitude. The wave just gets shorter, so this affects the wavelength. The last thing we're going to do is we are going to, let's see if I can slide it over here, take this 2, or this cosine 2x, I'm sorry, 2 times the cosine of 4x, add 1, which is going to mean that every y value is going to get 1 unit bigger than what it was before. So how that's going to affect us here is our graph is now going to go up 1 higher. Well, it did go up to 2, now it's going to go up to 3. It did go down to -2, now it'll only go down to -1. And before, the middle of the graph, if you look at the graph on the left, the middle of the graph was right there. What's going to happen is the middle of the graph gets moved up 1 unit as well. So now the middle of the graph, known as the midline, is moved up to y equals 1. Notice it's still going to run through its entire graph in a length of pi over 2. Okay, so we've got our pi over 4, our pi over 8, our 3 pi over 8. And all I'm going to do here is I'm going to put in my same y values. Now be really careful. Remember, over on this graph, that point was on the midline. It's still on the midline, but now the midline's there. At pi over 4, it's down at the bottom of where it's going to go. At 3 pi over 8, it's back on the midline, and at pi over 2, it's up here. And what it's done is it's shifted the whole graph up 1 unit. So there's how you can go about graphing step by step, taking one characteristic at a time, okay, to get a graph of a function where you have different coefficients at different points within the function. Now, one of the things that's going to be very important to be mindful of is if we have a set of data that graphs or behaves like this, where it starts out with the or the function hitting the midline. The midline could be there. If the midline was up here, then the graph would do something like this. But the point is, if the graph starts out at the midline, there, that is a hint that you want to use sine of x for your regression analysis. If you have a set of data where the data does something like this, and your midline is right here. Notice the data no longer starts at the midline. It starts at a maximum point or at a minimum point. Then you're going to apply y equals cosine of x. Okay, this is important. Be sure that you pay attention to this. If you need to go back through and listen to this a second, a third, a fifth time, whatever it takes, get this down. Because every time that we look at a set of data, you're going to need to decide, do I use sine or do I use cosine to model my data? That'll change everything. Okay, so be sure you get this right. Let's take a look at an example. Let's say we have a situation where, and I'm just going to take one out of the book so that you can reference it in the book. This is example 5, and this example is found on page 631. And what you're told is you have a company that makes ski coats, okay, some type of a winter coat for going skiing. And you're given information about their production pattern. You're told that during the month of October, they manufacture 9,000 coats per month. Now, clearly they don't need to be producing at that rate throughout the year. Who's going out to buy a ski jacket in August? Unless you're planning ahead. Okay. October for this company is when they produce the maximum number of coats. They produce the minimum number in April. And that minimum number they produce is 1,000 coats. Okay. My thought is realistically, their maximum is probably going to be around July or something like that because you have to have time to ship the merchandise out. And your minimum is probably going to be somewhere around December because they're going to be trying to get rid of last year's merchandise to prepare for the new styles for the upcoming season. But given this, you're told that this is a pattern that repeats annually. Okay, this is the way they run their company. Which says that we have a period of 12 months. Now, when we go to plot this data, what are we going to do? Well, we're going to have something like this. We don't really need to pay much attention in the negative direction, either X or Y. We know that the low point of this is going to be 1,000 units. The high point is going to be 9,000 units. Now, how do we find the midpoint? The midpoint is halfway between. Well, that's going to be the 9,000 plus the 1,000. Oh, we're just doing an average here, divided by 2. So our midpoint is going to be at 5,000. So the average number of coats they're making is 5,000. Okay, so let's take a look here. We're going to start in October. 6 months later is April. 6 months after that is October. 6 months after that is April. That would be actually 18 months. And 6 months later is going to be 24 months. So what we wind up with here is at the beginning, 9,000 units. 6 months later, we're at the minimum 1,000 units. 6 months later, we're at 9,000, 1,000, 9,000. So this gives us a production scheme that kind of goes like this. Really important here, our midline is right there. This tells us what type of function we need to select to model our production. You may say, oh man, I wasn't really paying any attention to that. Well, come back up here. If the data starts on the midline, you use sine. If the data does not start on the midline, you use cosine. And if you take a look here, do you see the data is not on the midline? So that means we're going to want to use cosine. Okay, so let's see what we have here. We've computed our midline, which is 5,000. We know that we want to use a model where we're going to have y is equal to a times the cosine of b times x minus c over b plus d. All right, we need to look up what these values are. Well, first, let's take a look at the graph. Above the midline, this thing rises 4,000 units. Below the midline, it drops 4,000 units, which says that we have an amplitude equal to 4,000. So let's start writing some of this stuff down. We have the period is 12 months. We now have an amplitude of 4,000. We have a midline at 5,000. And let's see how some of this stuff factors into the game we got going. Okay, first off, let's go back up. Our value A, there it is, up at the top, gives the amplitude. So what we're going to want to do is we're creating our graph, or our function down here. We're going to want y is equal to the amplitude. Well, that's 4,000 times the cosine. Okay, so we got 4,000 times the cosine. Now, we next want the period. Okay, the b value is going to be equal to the 2 pi divided by whatever the length of time is between a repeat. This is then going to give us pi over 6. In for b, we're going to put pi over 6. Times, now we have cosine x minus something or other. Let's see here, b's pi over 6. C is going to be how much is this shifted. Here, if we take a look, how much is this graph shifted left or right? Well, if you take a look at this graph that we have here, do you see that it hits its peak right at the start at 0? So we don't need to shift this left or right at all. We can just put in 0 there. And the last thing we need to do is to indicate how far this graph is raised above or lowered below the x-axis. Well, in this case, it's raised 5,000 units. This then gives us an equation to describe our production year after year, or this company's production year after year of coats. Okay, so now that we have that, we can start to answer some questions, just like we have in previous problems. We can do max and min, which we know already. The max is always going to be at October, and the min's going to be at April. So we really don't need to do that. But we could ask questions like, how quickly is production changing in any particular month? So for example, as you move from May to June, is the production going up or down? And how fast is it going up or down? Well, when you're talking about the rate of change, you need the derivative. So the first thing we're going to do here is we're going to compute the derivative. Y prime is going to be equal to, yes, this is going to be fun. First one I'm going to do is I'm going to copy this down, clean this up a little bit. We have our cosine. Now, inside's where I can clean this up. I'm going to take the pi over 6 and distribute it. So it's going to give me pi over 6x. Pi over 6 times 0 is just 0, so I'm not going to worry about that. Plus 5,000. Okay, so when it comes time now to take the derivative of this, that's a little bit cleaner than what we had before. The derivative is going to be, we're going to have our 4,000. Now when we take the derivative of cosine, that's going to be negative, and we're going to have the sine of pi over 6 times x. Remember, this is a chain rule, so I next need to take the derivative of this, which is going to give me a pi over 6 here. And then plus the derivative of 5,000 is going to be 0. So I can clean this up a little bit, and we're going to get y prime is equal to a negative 2,000 pi over 3 times the sine of pi over 6 times x. Okay, so here is our derivative. We don't need to necessarily locate maxes and mins, as we talked about before. Those occur in April and in October of each year. But what we could ask is something like the following. Okay, how quickly is production changing in December? Aha! If we're talking about how something is changing, that means we want to evaluate the derivative. In order to evaluate this derivative, we have to determine where December is relative to October. Let's see, from October to November is 1 month, from November to December is 2. Aha! What we're going to use here is x equals 2, as in we're 2 months later than October. So this allows us then to do the derivative is equal to this negative 2,000 pi over 3 times the sine of pi over 6 times 2. Well, this is equal to a negative 2,000 pi over 3 times the sine of pi over 3. You know what the value of pi over 3 is by looking at your unit circle. The sine of pi over 3 is going to be square root 3 over 2. So what this allows us to do is to rewrite this as a negative 2,000 times pi divided by 3 times the square root of 3 over 2. Hey, those 2's will cancel, and this will become minus 1,000. So what we're going to have here is a negative 1,000, and the way you would enter this into your calculator is a negative 1,000 times the square root of 3 divided by 3, which works out to be a negative 1,813 coats per month. So what this is saying is, through the month of December, production is declining by 1,813 coats. Okay, so that takes care of this particular section. Be sure you take a look at the homework and let me know if you have any questions.